All right, so 2002B as in Bubby. Okay. So back in the day, they used to give out two versions and declare that this was the alternate version with the B, but irrelevant, still the same. So we have lactic acid is a monoprotic acid that dissociates in an aqueous solution is represented by the equation above. A lactic acid is 1.66% dissociated in a 0.5 molar solution of lactic acid at 298. For parts A through D below, assume the temperature remains at 298. All right, so I want you to write the expression. That's a
First
toughie.
thing that's obvious is that lactic acid is very weak, like Christ's blood line.
Oh. So the Ka, I did. And it also, calculate its value. Okay. So we know we have a 1.66 and a 0.5. So 1.66% looks like this, 0.0166. And this equals X, which also equals your hydrogen. Clear out the memory, all the memories, such great memories. There we go.
Man, I love 1 plus 2 equals 3. That's my favorite number.
Maya's having a bad day. All right, so there's your X value. Since we know X, we want to use X. 0.83 squared. And we also will subtract by our known X. So we know the lactic acid is going to lose some of its starting amount. Oops, I don't want that. Let's do that. Square divided by parentheses 0.5 minus. So around 1.40 times 10 to the negative 4. If I did all my math correctly. Good, bad? Okay. All right. Part B says calculate the pH. Oh, this sounds vaguely familiar. So once we have our Ka value, we don't use it. Some of you like taking the last thing that's in your calculator and plugging it in. That would be bad. So let's plug in this. No, not that value. This value, since that equals our hydrogen concentration. So 2.08-ish. Okay. So there's our pH of our starting amount. Let's give that a little pizzazz. Okay. All right. C, calculate the pH of a solution formed by dissolving 0.045 moles of solid sodium lactate in 250 milliliters of the 0.5 molar solution of the lactic acid. Assume the volume changes negligible. Huh? It is. We're creating a buffer. So the first thing, we have our sodium lactate. Always show the dissociation of that critter. So the sodium will do nothing, but the lactate will behave. So we have 0.045 moles. So let's get a
Everything in this solution so far is in fact
edible. Okay.
I love that you didn't know that off the top of your head.
And 250 milliliters.
I'll let you know when it's up.
So 0.045 divided by 0.25. So 0.18 molar is our sodium lactate. So I'm going, and what are we looking for? pH. Yeah. All right. So looking at our, let's use a different color here. So we have our ice chart, which again is for organizational purposes. C3H5O3. There goes the calculator. So we've got 0.18 of that and 0.5. Yeah, 0.5. We'll say 0.5 since we're using 5% rule. And we're looking for this. Can we use Henderson Hasselbalch?
Yes.
Let's.
This should be a really question.
Yeah.
So whenever you're writing out that equation, does it matter if you start with the weak acid on the right hand side?
Okay, so what I'm hearing is, do I have to have hydrogen on the right side? The answer is yes, because my Ka has to have hydrogen or hydroxide on the right side.
So
Now,
you would have to use the inverse if you were to flip it.
If you're flipping it, then you're going to have hydroxide. So the things that I hope that you are referring to flipping is the lactic acid and the lactate. And that is perfectly legal. You can find a Kb value for the lactate. You can write the Kb expression, and then it'll be extra steps. But the answer in the end will be the same. So again, it's your preference. So, and again, Henderson Hasselbalch is also a preference that you may or may not partake in, but do realize those are your concentrations that you would plug in here as well, if you chose to go that way, which is fine. So pH is equal to pKa log of, and I'm hoping that I'm being a good example by using this equation enough that some of you are like, oh yeah, that's probably not a bad idea to have that. So the negative log of, we found that, 1.4.
During the test, Mark, can you just shout out Henderson Hasselbalch at random intervals to remind me to use it?
No. I shall not, will not. So we'll put our 0.18 and our 0.5 here. What'd you say, Jackson? I'm sorry. Well, you won't be in the same room with everybody else. And you won't have a calculator on Monday. Well, you will. So do you plan on coming in early to take part of the test?
I don't know.
Great story.
I'd probably just skip it.
Oof. This is being recorded, by the way.
So everything we say can and will be used against us in the court of law.
Absolutely. Without doubt.
Yeah.
Ooh, let's.
Does that
Are you
mean my?
promising to take each and every one of us to court?
If I have the time, I would love to take you all on a journey.
Does this mean
What's that? That'll work. Yeah. Yeah. Yes.
So if you don't use Henderson Hasselbalch and you just do it the normal way, do you have to show the KP?
No. Because you have concentrations for your weak acid. So you have concentrations for your weak acid and your common ion, which do appear in our expression up there.
When would you have to show the KP? Or do you at all?
If you have any hydroxide left over, or if we are, When you don't have both of these things, then yeah, but we do. So like if we titrated it with a strong base and we're at the equivalence point, we have to have another Ka or Kb value. Yeah. But this is a buffer, sadly. All right, so the pH went up as a result of adding the salt that behaves as a base. Things are looking great. Part D, let's erase some of that. Says a 100 ml sample of the 0.1 molar hydrochloric is added to 100 milliliters of our lactic acid. Adding an acid to an acid. Eesh. Calculate the molar concentration of the lactate ion in the resulting solution. Wow, that is a wacky question there. 100 milliliters of a strong acid is added to 100 milliliters of a weak acid. Okay. Thank God. When was this? 2002. Good Lord. Let's not ever add a strong acid to. Okay. So we have 100 milliliters. 1 liter. And that was 0.1? Yeah, 0.1 molar. So that'll give us, oh, I'm drawing a blank there. So 0.01 moles of HCl, actually a pure hydrogen, and 100 mils of the 0.5. 0.5. Oof. Okay, and what's my total volume here? 200. So I'm going to get a new concentration. So 0.05. So 0.25. Good Lord. I don't even want to write this. This is, ugh. HC3H5O3. Oops, wrong one. Dang it. 2.5. Do we have any lactic acid in there? Nope. So we'll say approximately 0. We're actually solving for that. All right. God, this is squirrely. So our Ka expression. That should be a 3, not a 5. Equals, what do we say, 1.4? So we're just rearranging. God, this dumb question. So we're going to switch that, and we're going to, oh, I should have put that value in. Sorry. Since we already had it, we didn't need to rewrite it. And we'll switch that. So now we've got our C3H5O3. Don't ask me why they asked this. This is just trying to see if you can use the Ka expression. 0.05. Oof. 7.01 times 10 to the negative 4.
I didn't get 0.01.
Well, I had 7.005287.
I just said 7.
Good enough. Close enough. All right. Yeah.
How do you know what to use X? Like, why is that?
Say that one more time. When do you?
You're supposed to use X.
Oh, okay. Up here.
Yeah.
I think she was like, instead of like subtracting the small sign.
In this one, we don't have anything to subtract by. Is that what you're referring to in part D? In what situation did you want to subtract or add X?
I don't know. I just didn't know that was like equal.
Well, these are horrible chemists putting a strong acid with a weak acid. So that's my first question. And none of these are going to like, we're going to assume that it's at equilibrium. I think it says it in the resulting solution. So that's at equilibrium. So if we're adding or subtracting X, you would drop it anyway because of the 5% rule. But honest to God, that's probably one of the dumber questions I've ever seen.
So do you want to use X?
Technically, yes. Or if you know what the value of X is, like in this case here, we know what X is. So we definitely want to subtract X on that. But
Since we're already at equal, we would have to do this.
sure. And that's why I only showed the E step here at equilibrium. Any others on this question? I think we had something very similar to this earlier. Okay, so let me stop this one and start another one.